Hello and welcome. In this video, we're going to take a look at a new kind of integral. It's a little bit similar actually to just taking the integral of a function in single variable calculus. Now back then we were just taking a look at taking an integral of something like f of x. And that's just taking a look as we go along the x-axis, essentially finding area under that function. Well, that was just following the x-axis. That's a path. Why don't we just take that same kind of concept and we can make that into a space curve in n-dimensional space. Now we can be integrating a function along a curve. Okay, well, there's a couple different kinds of functions that we might be interested in integrating along a path in space. So there's two kinds of line integrals that we're going to be looking at. One is going to be integrating a scalar function. That's going to be a lot more like what we were doing in single variable calculus, just integrating f of x dx. But we can also look at integrating on a curve going through a vector field, and that's where we have this interesting notation as well with capital F dot dr. Now let's define both types of line integrals and look at where we may be finding applications for each of these. Well, let's start off with scalar functions. Why don't we use an example in three-dimensional space? Now to start us off, we're going to need a curve. We'll call it C, and let's assume that C is a smooth curve. This could be really in any dimension we like. And let's assume that we have a function of that many variables. And so C is a smooth curve in Rn, and f is a function of n variables. Well, what we're going to do is, in order to sort of have a sum, a summation notation that turns into an integral, we're going to be dividing up this curve into little sub-intervals, just like we did when we were looking at the integral of f of x dx. But we're going to take each of these as being a small amount of arc length. So we're going to be using s's here exclusively. Each of these is a tiny little arc length, a sub-arc, let's call delta si. We're going to divide up into sub-arcs, I from 1 up to n sub-arcs, with the widths of delta si. Now in each of those sub-arcs, we're going to pick an arbitrary point. It could be sort of like a left endpoint or a right endpoint, remembering that, of course, our curve is oriented in the direction of increasing parameter, and that would be where we could get a left or right endpoint, or it could be a midpoint. It could be any point on that sub-arc. Once we've chosen that point, we can plug that into the function f and evaluate the function there. And then we'll take that and multiply by the width of each sub-arc and add them all together. This gives us a sum. The sum over all I of f of this arbitrary point xi star, yi star, zi star multiplied by delta s. And we can then start taking a look at making each of these subarcs get smaller and take the limit as delta si, all of them, go to 0. And what we end up from here is the definition of a line integral of a scalar function. The line integral of the function f of x, y, z ds over the curve C is this limit as the subarc widths go to 0 of the sum of f at each little test point times delta si, provided that this limit exists. And this is what it looks like in 3 dimensions, x, y, and z. Now how do we actually compute this? Because we really don't want to have to use the idea of Riemann sums through curves in space. Well, let's suppose that the curve that we have is parameterized in terms of t. So we have the function r of t over an interval from t equals a to t equals b. Then what we're going to do is we're going to change the variable of integration from s to match t. Using differentials, ds is equal to the derivative ds by dt times the differential dt. And ds by dt, by definition, is simply the magnitude of the derivative of r of t. That's perfect. And then with our function f might be a function of, let's say, x, y, and z. But what we can do is, since every one of the points is on the curve, then we can take our parameterization for x, y, and z given by the curve and substitute that into the function so that everything becomes a function of t. So we plug that parameterization in, and then, since we are integrating now with respect to t, we have an interval where t goes from a to b. And this becomes a nice definite integral with a single variable t. Now, what about in the case where we have, let's say, exactly the function of x, y, z? Another way that we could write this is to start off by replacing x with its parameterization in terms of t, replace y with its parameterization, and z with its parameterization, all given by the curve. And then for the norm or magnitude of our first derivative, we remember that the formula is simply dx by dt squared plus dy by dt squared plus dz by dt squared, all square rooted, and that will give us an integral in terms of t. And this is very similar if we have a function of two variables. Now, of course, the important question is here, where is this going to be applicable? Well, where this could be applicable is if we have maybe a thin wire, that would be like a path in 3 or maybe 2-dimensional space. We have a thin wire. Think about something that we might want to add up along its length. One thing we could do is we might want to start thinking about adding up sort of energy all the way along. Maybe that would be something applicable where energy is a scalar function. At every point, we can kind of say how much energy there is per centimeter of wire. Or another application is if we have something like linear density function. How many grams per meter of wire? As we go across this wire, then by adding it all together, we can get the total mass. So there's a couple little applications there that we can take a look at for an example. It's actually pretty nice to visualize this as a function of two variables, as thinking about the curve in the xy plane, and then taking a look at something like density at each of those points being a value along the z-axis. So, for the first little small piece of sub-arc here, we can calculate its density as kind of being sort of like the area of that little fence panel. And then going to the next section, maybe it's a little less dense here. You can see the z value is not as high. So to calculate the mass of this little section is essentially the area of this fence panel. And the density, as we go along here, is adding up all of these areas of fence panels. And essentially, it's like the area of this meandering fence, where we're taking the length of each segment, multiplying it by linear density to get mass. All right, well, here I've got an example, and I decided to be a little bit creative because oftentimes for simple examples, we like to use circular sort of shaped curves. And so a helix is a great idea, but we want to keep it maybe simple for an easy example and try to keep this on maybe just the xy plane. But I decided not to go with a circle. We've got an ellipse, and you're going to see that this makes some calculations a little bit more difficult. So buckle in, there's definitely a bigger integral coming up with a good review of several techniques of integration here. So we've got a thin wire in the shape of the right half of this ellipse, x squared over 50 plus y squared over 25 equals 1. We want to find its mass, and we're given the linear density function where the linear density at a point xy is simply equal to x. Now, this is the right half of an ellipse, so really we're saying that the density of this wire increases the farther away from the y-axis we are. Okay, well, we can handle that. Let's see if we can come up, first of all, with a parameterization. Well, since this is in the standard form of an ellipse, we can see the major and minor axes here, square root 50 and square root 25. So I'm parameterizing it just like a circle, except that I am adjusting x and y appropriately by the square root of 50 and square root of 25. And that gives me x equals 5 root 2 cos t and y equals 5 sine t. And since we want the right half, we're going to just maybe use a nice continuous interval from negative pi over 2 to positive pi over 2. All right, well, we'll be plugging this 5 root 2 cosine t into our linear density function to make it a function of t. But then in order to set up our line integral, we're also going to need to find the derivatives dx by dt and dy by dt. So here are those first order derivatives, dx dt, dy dt, and I've squared both of them so that we can set up the equation for mass. Mass is simply the line integral over the curve of the linear density function. And then to change the variable to t here, we will plug in our parameterization for x and y, and then multiply by the square root of dx by dt squared plus dy by dt squared. All right, well, starting off with the fact that the linear density function is simply x, then we have 5 root t cos t. And we'll pull that constant 5 root 2 out. We also have a factor of 25 that we can pull out of the square root to get 5. And that's going to make its way out to the front as well. Now, if we have 2 sine squared t plus cosine squared t, we could use a little identity here. Cosine squared t is simply equal to 1 minus sine squared t. So putting the pieces together, we have 25 root 2 as a nice constant. The definite integral of cosine t times the square root of sine squared t plus 1 from negative pi over 2 to positive pi over 2. Okay, well, at this point in time, we still have a bit of a challenging integral. We'll start off with a u substitution. And every time I'm making a new substitution, I'm going to change colors because, well, unfortunately, there's going to be more than one of them here. So the u substitution that we might want to try is letting u equal sine t, and that's going to give us du over cosine t to replace dt. That's great, because that's going to cancel out this cosine t here. So what do we end up with? Make sure to change the interval as well. By plugging negative pi over 2 and positive pi over 2 into sine t, our interval will change to negative 1 and positive 1. And now we simply have the square root of u squared plus 1. Okay, well, it's definitely looking a little tidier with these particular variables now that we've got u. Unfortunately, this is still a little bit challenging. Trying to find another substitution to work here is going to have to involve trigonometric identities. We're going to have to use a strategy where we use a trigonometric substitution, which means we're changing the variable again. Whenever we have the general form of u squared plus 1 in a square root like this, it might be a good idea to let u, in this case, equal tangent theta. And that's going to give us an identity to use. Tangent squared theta plus 1 is equal to secant squared theta, and then the square root of secant squared theta is simply secant. But we do have to remember to change the du, our integrating variable, and du is going to equal the derivative of tangent, secant squared theta, d theta. Once again, don't forget to change the interval of integration as well. By plugging negative 1 and positive 1 into tangent, we end up with negative pi over 4 and positive pi over 4 as being the new interval for theta. Oh boy, okay, so we're going to simplify this square root. The square root of tangent squared theta plus 1 is simply the square root of secant squared theta, and that is secant. So we're going to end up with an integral of secant cubed theta. Okay, now, at this point in time, you can see that this is just going on, and every step of the way, we're trying to make this look like a slightly more simple integral. And even this is looking great. Secant cubed is fairly nice and straightforward, but at this point in time, you might not really remember how to integrate secant cubed theta. So I would recommend, since this one does come up periodically, you probably will have found that there's a nice table of integrals to come to your aid at this point in time, where you take a look at how to integrate sine squared, cosine squared, tangent squared, powers of the trigonometric functions like that. And you might not see it right away, but if you look it up, they might be able to find in a table of integrals how you can get the antiderivative of secant cubed theta and get us out of this substitution process over and over again. All right, like I said, not the greatest example here because it just continues to go on, but the antiderivative of secant cubed theta is secant theta tangent theta plus the natural logarithm of secant theta plus tangent theta. To get from that step to the next step, I just use a table of integrals, but you can also do that by hand. It just involves some very interesting trigonometric identities that you may not have much use for otherwise. At this point in time, we can evaluate, and we're kind of lucky. Pi over 4 and negative pi over 4 are pretty nice values to plug into secant and tangent. And here are those values. Don't forget, there's lots of negative signs to worry about here. And, well, we have two terms that collect nicely. Root 2 minus negative root 2 is 2 root 2. Well, that's going to be very nice because we have a 2 that's going to cancel when we distribute that on. And root 2 times root 2, we're also going to end up just getting an extra factor of 2. But there's even more simplification that we can do. It's when we start collecting terms and distributing negative signs that we end up seeing two very similar logarithms. And we have this negative sign in front of the logarithm of root 2 minus 1. Remember that if we want to bring that negative sign in and make this a positive, then we'd end up with the reciprocal. And if you think about that for a moment, 1 over root 2 minus 1, if we take that 1 over root 2 minus 1 and multiply top and bottom by the conjugate, root 2 plus 1, then we'll end up with root 2 plus 1 over root 2 squared. Minus 1 times positive 1 would be minus 1. So we just end up with 2 minus 1 in the bottom, which is 1. Which gives us root 2 plus 1. So what's really strange here is when you bring this negative sign, want to bring this in here and write this all to the -1 and make this a plus sign, you end up with two of the same logarithms. The natural logarithm of root 2 plus 1 plus, and this simplifies to the natural logarithm of root 2 plus 1. So there's two of those as well. All right, like I said, lots of simplification. You can check each of these steps along the way. Now at this point in time, everything's got a nice common factor of 2 to cancel the 2 in the denominator, and I can distribute 25 root 2 onto each of these terms to get the final answer in about the simplest form possible. Our mass is 50 plus 25 root 2 times the natural logarithm of root 2 plus 1. It's not a nice number. It took us a long time to get there. It's a really good chance to review all kinds of strategies of integration, and you can understand why a lot of questions out of textbooks tend to use nice circular paths, because a circular path will tend to have some nice values when you take a look at the magnitude of r prime of t. Sometimes you just get a constant that way, but it's not always going to be the case. So I thought I'd throw this one in there, even seeing in advance it would take a little while. And if you have a computer with Maple or some other application installed, well, you can shortcut a lot of the integral once you get the idea of how to set it up. Now, even though this was an example that was simply in R2 with just x and y and a curve on the xy plane, really just trying to do the same sort of application in a third dimension, having 3 variables and a curve in R3 would be the same sort of process. We'll just end up with an integral that we have to solve in terms of t. Now, before we move on to our second form of line integrals, there are a couple properties that we should maybe just take a look at. The first property is if we are going to be integrating the function just equal to 1 over a curve. Well, then since this is simply just 1 and ds is equal to the magnitude of r prime of t dt, this is simply going to be the same calculation that we use to find the arc length of the curve. And another property, especially thinking in terms of mass and linear density, it doesn't matter if we are adding forward or backwards. If we're going in the direction of this curve C, or if we're using the opposite orientation, here is that's just denoted by -c, going backwards along the same curve, we should end up adding up the same value. It doesn't matter how we add up the density to get mass, we should get the same result. All right, going back to our two forms of integrals, let's take a look at line integrals of vector fields now. And for this form of line integrals, again, we're going to start off with a nice smooth curve in Rn. However, this time, instead of having a function, we're going to have a vector field. So let's let f be a continuous vector field on some region of that space that contains the curve. All right, well, here I have a visual representation of that oriented curve. And then at every point along that curve's path, we can visually represent the vector field as these green arrows. And what we're going to be doing, much like last time, for a line integral, we're going to start by kind of forming a sum. We'll start by dividing C into subarcs. But this time, instead of thinking about the length of each subarc, let's take a look at trying to represent each subarc by a vector. So they're not quite straight lines, but what if we were to try to represent each of these subarcs with a vector? Well, what we could do to get that vector is remember that we have our origin somewhere here, and every point on our curve is represented by r of t. So if this is going to be arc interval number I, then let's say that the end point of this subarc is going to be ri of t, kind of like the right-hand endpoint, left-hand endpoint, or really not left and right, but thinking about initial and terminal. The initial, let's say, would be r sub I minus 1. Okay, well then the purple vector is simply a change in position, which is ri minus ri minus 1. And that's displacement, really, if you think about it. It's a change in position. Now we can get an idea maybe of where this can be used for, especially looking at capital F. Maybe what jumps out at you would think force. If this is a vector field representing force, and we are taking a look at displacement, then the dot product of force and displacement gets us work. And we can find the work in each segment of this curve and add it together to get the total work. So that's what we're going to do here. We're going to consider a sum where we take the dot product of the vector field at each position multiplied by the displacement. And then we're going to start taking shorter and shorter little subarcs and shrink them to 0 length. And that's going to be where we bring in the limit. And that gives us the definition of the line integral of a vector field. You can see it's very different notation from a line integral of a scalar function. We have f dot dr. dr is this little delta ri getting shrunk down to 0 length. That's where we get that. But it's a dot product. So here's that limit as delta ri goes to 0. Now, we're not going to want to compute it this way. So what's the computational form of this? For computational form, we can rewrite dr as being dr by dt. So simply just r prime of t. We're going to take our vector field function, plug in the parameterization of points on our space curve, use the dot product with r prime of t. It's a vector, dot product with a vector. Well, that's a scalar function once you've evaluated that, and we're just going to be taking a look at integrating it with respect to t. And we should have some sort of interval here from a to b for t. And another way to write that, if our function is in R3, we would have the parameterization x of t, y of t, z of t, and the derivative x prime, y prime, z prime. When we dot product these two things, we'll end up getting a function of t and integrate from a to b. That would be our interval. Now, because we are thinking about dot products here and looking back at this visual representation, if we were going in one direction, dot producting it could be a positive value, and the dot product could be a negative value in the opposite orientation. So this is an oriented integral, and that's one of the couple properties that we should probably list here. This property, where we would take our curve and change the orientation, is simply the same value, but just a negation. And that should kind of make sense. Work in one direction, negative work in the other direction. And as well, another application, this is an interesting one. By taking the dot product of f dr, we could always write this as a scalar function of f dot t hat, the unit tangent vector. By doing that, we can actually rewrite this as a scalar function and have this as now a line integral of a scalar function. So there is a nice relationship between the two. Well, let's try a three-dimensional example of a line integral of a vector field. And we'll try to keep this one a little bit more on the simple side. Let's keep this one nice and circular. Let's look at the line integral of f dr, where f is the vector field negative y x2. Okay, so that the z component is always constant. And c is a circular helix. Trying to keep this one circular and not elliptic. Okay, well, this is a radius of 5, spinning counterclockwise around the z-axis, and z increasing proportional to t, where t is from the interval 0 to pi. Well, it's pretty easy to plug these into our vector field f, so we'll hold on to that for a moment. We are going to need to compute dr by dt. R prime of t is simply going to be the vector dx by dt, dy by dt, dz by dt. So for our circular helix, negative 5 sine t, 5 cosine t, 1. All right, let's evaluate this line integral. So taking our vector field, negative y, x, and 2, we will plug in points on the helix. For y, 5 sine t, and for x, 5 cosine t, and there's nothing to plug in for z. Z doesn't show up as any part of the function for our vector field. We need to dot product that with r prime of t, and that will allow us to write this in terms of dt. We are going to integrate from 0 to 2 pi. All right, well, the dot product is now going to get us a nice scalar function of a single variable. And then we have a very nice identity. And so this integral very quickly fizzles out and becomes a very easy calculation at the end. And so you can see why it's so nice sometimes to use circular helixes. Now, what about that vector field I chose? I also deliberately chose that so that this would hopefully be fairly straightforward. If we take a look in Maple and visualize both the field and the space curve, you might get a good idea as to why I chose these two things for this example. All right, well, over here in Maple, I've got a couple of my favorite packages, vector calculus and plots. And I've got that nice helix with a radius of 5, oriented counterclockwise, going upwards along the z-axis. And you can see that red spiral. Now, here's my vector field, negative y, x, and 2. Now, if x and y are positive, looking down at the xy plane, that would be quadrant 1, then our vectors are going to be pointing, well, I guess, left and up. Now, if I'm in this second quadrant on the xy plane, at this point in time, I'll have negative x and positive y. My vectors are going to be oriented left and down. And repeating this for all 4 quadrants, you should see this is actually going to generate a circular field. And this z component is always pointing upwards. So taking a look down, the z-axis is right here in the center. These vectors are all oriented counterclockwise in the same direction as our helix. So thinking about having our dot product, it might be a fairly easy calculation. All of my vectors are going counterclockwise along with the helix. They're not quite parallel because of the z-axis. You can see here at various different points. Maybe I'll have to zoom in a little bit. Looking along this curve here, these vectors are not perfectly parallel. And here's a green arrow and a red curve. It's hard to see them both, but they're not exactly parallel. They're not tangent anyways. Our helix has a z component velocity of 1. If you want to think about that as velocity, its derivative. But these are going to be vectors with a z component of 2. So they're never going to be perfectly tangent. They're very close. Anyway, that's kind of why I chose this. I kind of figured if I had a field that was going in the same orientation of a helix, it should make some calculations fairly straightforward. And sure enough, when we're taking the dot product of some of these nice circular motions like this, we're going to start to see that things simplify a great deal. Well, hopefully that gives you a little idea of how to evaluate a couple different forms of line integrals. We've got the scalar function and we've got a vector field. Your goal is to essentially take that parameterization of the curve and use it in a way to change each of those kinds of line integrals into a single variable integral with dt, and then integrate over an interval of t to get your answer. Now the main applications there, we've got to remember, with scalar functions, one big application, since we're adding along an arc length, maybe if we're adding up a linear density function, we can get mass. And actually from that, you can do other calculations like find the center of mass. And a big application of integrating over a curve with a vector field. Well, if we look at dot products, then we can kind of interpret that as a force multiplied by a displacement. We've got the dot product there, that's going to represent work, and you can get the work done through moving that particle through that field. All right. So now that we have a couple visualizations, we can do some more with line integrals in the future. Thanks for watching, and I'll see you in the next video.